Discover how fluids can remember their past motion, creating mysterious ripple effects that persist through time. When a droplet moves through fluid, it creates ripples and vortices that don't disappear instantly but persist, influencing future motion. Let's start by understanding what makes this phenomenon so unusual and counterintuitive. In typical fluid dynamics, we assume fluids respond instantaneously to applied forces. However, in confined microfluidic systems, the fluid's past motion continues to influence its current behavior. As a droplet moves, it leaves behind a wake of vortices and disturbances that persist much longer than expected. The force at time t depends not just on current conditions, but on an integral over all past velocities. The key lies in how momentum diffuses through viscous fluids. When a droplet moves, it generates swirling vortices in the surrounding fluid. In systems with moderate viscosity, these vortices decay slowly rather than disappearing instantly. The droplet is surrounded by layers of rotating flow that persist and influence later motion. The decay time scales with length squared divided by kinematic viscosity. In microscale systems, this decay time ranges from milliseconds to seconds, enough to create memory effects. One of the most striking examples is the walking droplet experiment. In a vibrating fluid bath, droplets bounce on the surface and create standing waves that guide their horizontal motion. The droplet creates waves beneath it, then literally surfs on its own wave field in a continuous feedback loop. Each past bounce contributes to the wave pattern, and this accumulated pattern guides the droplet's future trajectory. The droplet's path is a function of both its current state and the entire history of waves it has created. Remarkably, this classical system mimics quantum pilot wave behavior, showing interference and tunneling-like effects. Let's look at the mathematics behind hydrodynamic memory. The equation of motion includes both external forces and memory forces from past motion. The memory force is expressed as an integral over all past times, weighted by a memory kernel gamma. The memory kernel typically decays exponentially with a characteristic time tau, showing how older history matters less. This type of memory force is known as the Bassett history force in fluid mechanics. Several physical mechanisms create and maintain hydrodynamic memory. First, viscous diffusion spreads momentum slowly through the surrounding fluid. Second, confined geometries trap vortex structures that would otherwise dissipate. Third, surface waves can persist with decay times much longer than typical flow timescales. In confined spaces, the fluid has nowhere to escape, so disturbances recirculate and persist. Memory timescales either with viscous diffusion time or with wave oscillation period, whichever is longer. Hydrodynamic memory has important applications in modern technology. Micro-robots can exploit memory effects to swim more efficiently by riding their own wakes. In drug delivery, understanding memory helps control how particles navigate through blood vessels. Multiple particles can synchronize their motion through shared memory in the fluid medium. In biology, cilia and flagella coordinate their beating through hydrodynamic memory, not direct contact. The walking droplet system reveals a surprising connection to quantum mechanics. Classical walking droplets exhibit behavior similar to quantum particles, including interference patterns. These droplets demonstrate double-slit interference, tunneling through barriers, and quantized orbital states. This resembles pilot wave theory, where particles are guided by an underlying wave field. This suggests that quantum-like behavior can emerge from deterministic systems with memory. Hydrodynamic memory challenges fundamental assumptions in fluid dynamics. Classical fluid dynamics assumes force and velocity are related instantaneously through viscosity. The standard drag law says force equals negative gamma times velocity, implying instant response. But memory effects show that force actually depends on the entire history of velocity changes. The correct form includes an integral over all past velocities, weighted by a memory kernel. Time flows forward, but the fluid carries information backward from past to present. The fluid transforms into a viscoelastic storyteller, weaving past events into present dynamics. Let's summarize this remarkable phenomenon of fluid memory. Fluids remember their past motion through persistent vortices and waves that don't instantly dissipate. The memory timescale depends critically on viscosity and geometric confinement of the system. This has profound applications in micro-robotics, biological systems, and even quantum mechanics analogs. The droplet and its surrounding field form a unified system where past continuously shapes present. Even the most fleeting substances, like fluids, possess a form of persistence and memory. Every drop carries subtle whispers of its past journey through the fluid medium it inhabits. Explore how fluids remember past motion at the microscale and why this changes everything in microfluidics. When you push a droplet through fluid and stop, it doesn't stop immediately. It glides, overshoots, as if the fluid remembers your nudge. Let's understand what hydrodynamic memory actually means at the microscale. You nudge a tiny oil droplet in water and stop pushing. Instead of stopping, it glides and overshoots slightly. This memory lives in slowly diffusing vortices, the droplet left behind in the fluid. Many microfluidic models assume instantaneous drag where force now directly equals velocity now. But with hydrodynamic memory, the flow lags and present motion depends on the entire past trajectory. Vorticity spreads by diffusion with kinematic viscosity nu. A disturbance travels out to a thickness delta of T equals the square root of nu times T. In water, nu is about 10 to the minus 6 meters squared per second. After 0.1 seconds, delta is the square root of 10 to the minus 7, approximately 3 times 10 to the minus 4 meters, or 0.3 millimeters. That's huge compared to a 10 micron droplet, so its own wake can feed back for a long time. The drag force actually depends on the entire history of motion, through a history force term. When you give a bead a sudden push, right after the change the boundary layer is thin and shear is large. As time passes, the boundary layer thickens, and the extra drag decays slowly with a long tail. The classic Stokes drag is 6 pi mu AV, but this misses the history after effect. The Bessel-Boussinesq theory adds a history force with a kernel proportional to T minus tau to the minus 1/2. Recent past weighs more, but distant past still counts. The viscous timescale tau nu is defined as a squared over nu. For a 5 micron particle, tau nu equals 25 times 10 to the minus 12 over 10 to the minus 6, which is 2.5 times 10 to the minus 5 seconds. At t equals 10 to the minus 4 seconds, the ratio of history to Stokes drag scales like the square root of tau nu over t, which is about 0.5. That's a 50% correction, big and long-lived. When you accelerate a particle, you're also accelerating some of the fluid around it. Moving a sphere in water is like moving the sphere, plus some of the water stuck to it, so quick accelerations feel heavier than steady motion. The effective inertia includes added mass, altering transients, resonance, and control. For a sphere, the added mass is 1/2 rho f times v, which equals 2/3 pi a cubed rho f. For a 10 micron particle in water with density 10 cubed kilograms per cubic meter, the added mass is approximately 2.1 times 10 to the minus 12 kilograms. A 10 micron oil droplet with density 900 has mass about 3.8 times 10 to the minus 12 kilograms, so the ratio of added mass to droplet mass is about 0.55. The fluid's inertia is comparable to the droplets, so transients cannot ignore it. This visualization shows the particle and the effective added fluid mass moving together as one system. Thermal fluctuations don't decay exponentially as simple models predict. They have algebraic long-time tails. Track a micron bead's thermal jiggling. Its velocity autocorrelation doesn't die off exponentially. It has a t to the minus 3/2 tail. Fluid vortices keep poking it even at long times. This breaks simple Langevin models and affects diffusion estimates and microrheology measurements. The crossover time is roughly the viscous diffusion time over the bead radius. Tau nu equals a squared over nu. For a 1 micron bead, tau nu equals 10 to the minus 6 squared over 10 to the minus 6, which is 10 to the minus 6 seconds. At t equals 1 millisecond, for times much greater than tau nu, the residual correlation scales as t over tau nu to the minus 3/2, which equals 10 cubed to the minus 3/2, about 3 times 10 to the minus 5 of the short time value. This graph compares exponential decay to the algebraic t to the -3/2 tail. The algebraic tail decays much more slowly. Let's summarize how hydrodynamic memory changes microfluidics. Vortices diffuse slowly, so memory lasts much longer than the particle size would suggest. The history force means drag depends on the entire past trajectory, not just current velocity. Added mass makes the fluid's inertia comparable to the particle's own inertia. Long time tails mean thermal fluctuations decay algebraically, not exponentially as simple models predict. The fluid remembers the past, and that memory shapes the present motion in profound ways that matter for design and measurement. Explore how fluid memory affects droplet motion in confined channels and microfluidic devices. When droplets move through microchannels, they leave behind fluid wakes that persist and influence future motion. In narrow channels, walls trap vorticity and extend memory effects over many droplet diameters. In a 50 micrometer channel, a droplet's wake cannot spread indefinitely because walls reflect and absorb vorticity. The droplet re-encounters its own flow field for extended distances, creating history-dependent behavior. Memory time scales as channel half-gap squared, divided by kinematic viscosity. Let's calculate memory time for a channel with 25 micrometer half-gap. This gives a memory time of about 0.6 milliseconds. At 10 millimeters per second velocity, the memory length is about 6 micrometers, roughly 1 droplet radius. When driven oscillatorily, particles experience complex impedance that depends on frequency. Drive a bead sinusoidally. At low frequency, it follows the force, but at high frequency, it lags and feels stiffer. The fluid plus memory acts like a visco-inertial impedance, creating phase shifts between force and response. The hydrodynamic impedance includes steady drag plus history corrections proportional to square root omega. The Womersley parameter alpha equals droplet radius times square root of omega over nu. For a 5 micrometer droplet at 500 Hz, alpha is about 0.089, giving 9% corrections to Stokes drag. Droplets interact through their slowly decaying wakes, creating drafting and pairing effects. Two droplets in line show drafting. The follower speeds up and the leader slows due to wake interactions. In a channel of width W, the slowest lateral vortex mode decays exponentially with this time constant. For a 100 micrometer wide channel, let's calculate the decay rate. This gives a decay rate of about 990 per second. The wake persists for about 1 millisecond, during which a droplet travels roughly 10 micrometers. Step responses and frequency sweeps reveal clear signatures of hydrodynamic memory. Apply a tiny square wave pressure to a droplet and record its velocity over time. With memory, the response shows a t to the -1/2 shoulder after each edge, not an instant jump. Fit the step response with this form to extract memory time tau nu. With a 3 micrometer radius droplet, tau nu equals a squared over nu, giving 9 microseconds. Sampling at 100 kHz resolves the early decay regime clearly. Understanding memory helps optimize microfluidic devices and avoid unwanted interference. You can exploit memory for wake-assisted pairing or use phase lead actuation to boost transport efficiency. In droplet sorters, back-to-back kicks interfere because the second kick rides the first wake and overdeflects. Keep actuation period much longer than memory time to avoid crosstalk between successive operations. Memory time scales as droplet size squared over nu near the droplet, and channel width squared over nu when wall limited. Keep actuation period t much greater than memory time to avoid unwanted interference. For a 10 micrometer droplet in glycerol water mixture with nu equals 10 to the -5 meters squared per second. Memory time is 10 microseconds, so actuation should be spaced at least 100 microseconds apart to avoid crosstalk. Hydrodynamic memory creates time-delayed interactions, crucial for microfluidic design. Walls confine vorticity, making droplets interact with their own wake history over extended distances. Oscillatory forcing reveals complex impedance with amplitude and phase corrections from memory effects. Smart design either exploits memory for enhanced function or avoids it through proper spacing and timing of operations.